All right, so this tutorial is a quick overview of all the different ways you can take white light from various sources and separate out the colors that are mixed in with them. There are 5 or 6 different phenomena that you want to understand and then be able to match that with a particular phenomenon, let's say rainbows or colors of oil slicks, etc. Okay, so there's no math that's involved in any of this. It's descriptive. We will have talked about a lot of this in the PowerPoint presentation, so this is a summary and maybe even get us a little beyond that. Okay, so I'm just going to go through these quickly, get in some vocabulary, and then we can talk more about with demonstrations and PowerPoints. Okay, so background. Color in itself does not exist, and that's an important thing always to keep in mind. Color is a construct of your brain, and it's how your brain interacts with your eye and how your eye receives input of light and, of course, the light sensor cells it has. Some people are colorblind. There's a number of animals that have no sense of color except for black and white. So we want to understand that it doesn't exist, but we can still talk about it. So it's a construct of your eye and brain. Okay. Most light sources are polychromatic. In other words, they contain all the colors, red through violet. Some contain more blue than others, let's say like fluorescent lights. Some are more yellowish, like incandescent bulbs. All right, but when you have all or most of the colors, they appear to our eye as white. And then I don't have a space for this, but the absence of any light would then be black. Okay, so how do we get the colors therein to show themselves? All right, so the first one is the most common, and that is pigmentation. All right, dyes, paints, etc. Okay, what they will do is they will absorb certain colors and reflect the rest to our eyes, okay? And this assumes, this is important, that the light source is white light, which I guess we already said is a default assumption, okay? So there's 2 ways we can look at how we can get different colors to come out through pigmentation. There's color by addition of light. Actually, I should be careful what I'm saying because that's not technically pigmentation, but it fits in this general idea. You take a mixture of different intensities of primary colors, and every color under the sun will be can be produced. So the primary colors again are red, green, and blue. And then when you mix red, green, and blue in equal intensities, red and green, red plus green equals yellow. Right? We can mix blue plus green equals cyan, and we can do blue plus red, and that equals magenta. So those are combinations you're worth understanding. Okay, so I'm not going to say anything more about that. All right, we're more interested with the pigmentation is color by subtraction of light. Okay, and that's also with filters. The idea is light strikes a pigment. Pigments themselves do not have color. The molecules that make up the pigment or the dye do not have color. What they do, though, is they will absorb particular frequencies or wavelengths based on a resonance effect, and others are reflected. Okay, so for example, this paper or the paper you're looking at appears white because it reflects all colors, but the ink itself appears black because it reflects none of them. Right? So that's the simplest case of that. And so you have in front of you, or I'm going to refer to a pigment wheel, where I have the secondary colors, yellow, magenta, cyan, and where they overlap, you will get a red-orange, or a green, or a blue/violet. And what's happening is, when I overlap, let's say the yellow and the blue pigment appears yellow because it only reflects green and red. Okay? In other words, it absorbs blue colors, and so what reflects to our eye are green and red, or our eye perceives that as yellow. Now, if I overlap that with cyan, cyan appears cyan because it absorbs red and only reflects blue and green. So if you will, I'm going to put next to this what it reflects in the yellow are green and red, and this reflects, cyan reflects blue and green. So when I overlap them, the only one that can reflect from both of them is green, so where they overlap is green. So that's color by subtraction. It's a little bit complicated, but we'll work some of these out in class, especially with filters. Okay, let's move on to the next means for bringing out light. It's not often you see this, but it's found in nature with rainbows and such, and that's refraction and dispersion. Okay, so there's two phenomena going on here. The refraction, we know what that means. Dispersion is the separation of the colors because of that. And it's based on the fact that within a medium, different wavelengths have different indices of refraction. Okay, and that's a little bit different than when we learned refraction. We learned refraction was about the incident angle and the medium in which it travels. So in this diagram below right here, we have white light, which has all the colors in it, hitting at an angle, which is the same for all the colors. It's entering the same medium for all the colors, yet we have this dispersion effect, the separation. So what that implies is that if red refracts differently than violet, it's because red has a different index refraction of violet just because of its wavelength. Okay, so different wavelengths have different indices of refraction, thus causing the various colors to refract at different angles and therefore separate. Okay, so this explains rainbows, waterfalls. What I mean by that, if you look through a waterfall with all the mist, you'll see a nice rainbow usually. If you have crystals and you have light shining through them, they're cut in such a way that you get little spectra of light. You get aberrations in lenses and glass, which can be an issue, and we'll talk about that and demonstrate that in class. Okay, so what you want to know about this diagram here, that white comes in and the colors come out, is notice that red bends the least. So this has the lowest end, lowest index compared to violet because it refracts the most. So it will have the highest index of refraction. And then, of course, the other colors will be between them. The reason we use a prism is because you get more separation because it will refract twice, upon entering and upon leaving. So it will enhance the small differences in index of refraction. The next diagram right here shows raindrop and how rainbows form. So one might think that if the sun is here, then we would have to be here in order to see the light separate out. It's not quite that simple. Okay, so what happens is when the white light enters the raindrop, it starts to disperse, refract and disperse, internal reflection right here. Separates even more, and then in order to see, your eye is here, and it might look up at an angle and pick up blue light. If it changes its angle, it might pick up red light, and different angles correspond to different colors that reach our eye, and then we put it all together, and you get a nice little rainbow. But the point you just have to know is that it's a refraction and dispersion effect. And I already noted that violet bends the most, indicating that it has the greatest index. Okay. The next phenomenon that we can use to bring out color is interference. And this is something we've already talked about in some detail, so I'm just going to review it but not go into all the specifics because we've done that before. Different colors constructively or, let's make sure we're clear, destructively interfere due to path differences. This explains colors from diffraction gratings, those great things we did a lab on in the glasses, CDs, soap bubbles, and oil slicks. Okay, so there's two ways we can cause waves to behave so they'll interfere. There's interference due to diffraction. Okay, and again, we've talked about that. Right? You pass white light through multiple slits or even single slits, and you'll get different wavelengths diffracting different angles, and therefore, due to path differences, some will constructively interfere at one spot, destructively interfere, etc. And then we have thin film interference, which we also went over in some detail. But note that that's the difference. Here you're using reflections off of a transparent layer of, I'm not sure what this is supposed to say, transparent layers of water or matter or material, maybe. Okay, but you get the idea. So review that. So let's finish up with the 5 minutes we have left. Let's get to the last one, which explains a lot of other phenomena. So this is in general called absorption, transmission, and scattering. Okay, and this explains a lot, especially in our atmosphere. So the idea is when, in general, this is a general statement, when light is incident upon a medium, it either transmits meaning the medium is transparent. In other words, the wave, the light goes completely through. It is not impeded in any such way by the medium. Or it is absorbed. There's the exact opposite of transmission, making the medium opaque. Okay? Or it is scattered in all directions. Scattering is actually a fairly complex process. You can think of it as like a diffuse reflection where light comes in and it's reflected in all directions. It's a little bit more involved than that, but we can leave it at that for now. So let me give you an example in an atmosphere. Our atmosphere is transparent, okay, to visible and radio, as we mentioned before, but opaque to most ultraviolet because of the ozone and infrared due to certain greenhouse gases, and that leads to global warming. Visible light will scatter off of air molecules, water droplets, and ice crystals. So I want to explain that scattering part, okay, in a little bit more detail. And what determines the transmission or absorption or scattering, okay, is the frequency of vibration of the molecules or the objects that the light is hitting. Okay, so everything jiggles with a certain frequency, and light has a frequency associated with it, the various colors do. And so if there's a matching of those frequencies, we get a resonance, and that resonance leads to absorption. If there is no resonance, then it will pass right through it as if it's not there. That's really what it boils down to. And scattering also comes from an absorption type thing. So let's take a few minutes here and explain the rest. So in the atmosphere, we are primarily nitrogen and oxygen molecules, and they vibrate with the same frequency as blue and violet light. They do not overlap red or orange or yellow very much. So what happens is if they vibrate the same frequency, those molecules will absorb the blue and violet. They don't hold on to them. What they'll do is, rather than become excited, they will just re-emit them in all directions, and that's what scattering is. Okay, so thus they are scattered in all directions. Thus, the sky appears blue, and to a lesser extent, a really deep blue, in all parts of the sky because light is being scattered in all directions, so no matter which way you're looking at, you're seeing light, scattered blue light. The only place where you won't see the sky to be blue, at least during the normal daylight time, is when you're looking directly in the vicinity of the sun. When you're looking directly in the vicinity of the sun, very little light is scattered. It gets through, at least the oranges and yellows and the greens, so that light coming in the vicinity of the sun appears yellowish or even clearish. So next time you're outside, especially in the summertime, look in the general vicinity of the sun, the sky appears kind of whitish, a little yellowish, and then off to the sides, it's bluish where all the scattered light has gone. Okay, and again, why is blue preferentially scattered? Because this it vibrates, or it has the same frequency as the vibration of those particular molecules. Now, at sunrise or sunset, a similar effect happens, but it gives rise to a very reddish orangish sky. So if you look at this diagram right here, what's key about sunrise or sunset is there's so much more atmosphere to travel through. So when the light comes through, the blue and the violets are going to be scattered, but they're not going to be scattered towards us. They're going to be more scattered in other directions. So they're not going to even reach our eye. So what reaches our eye are reds and oranges. Okay? So it's the same effect as we see here, but because the sun is at the horizon, the light that's scattered away is not going to reach our eye. It's going to be away from it. And the same is true at sunset. So at sunset, sunrise, lights that travel through more atmosphere, the blues and greens are scattered away, leaving red and oranges, but primarily reds to get through our eyes. Clouds and dust on the horizon enhance this because they cause the red to diffract. And since they diffract, they're going to even spread out more and take up more of the angle or the field of view of the sky. Okay? And the last little thing I'm going to say before we run out of time, the same effect explains why clouds and ice crystals appear the way they do. Now, they're made up of transparent material, but because they are very different sizes, they vibrate at multiple frequencies. Consequently, all the colors overlap them and are scattered, and therefore, if I'm reaching all the colors, they're going to appear white. Okay, so the light just doesn't simply pass through them, they scatter off of them, and all scatter, and we get white light. So I'll finish up the rest in class.